Hello, everybody. Welcome to the last section of chapter 5, section 3, the Poisson distribution. This distribution is it deals with a whole different category of discrete probability distributions. In section 1, we dealt with the general discrete probability distributions. In section 2, we dealt with binomial probability distributions, which there are only two possible outcomes. Now we're going to look at a whole different type of category. And this one has a lot more valuable meanings that we can use. It's used by weathermen. It's used to predict future occurrences of weather based on past performances. It's used by aircraft industry, and especially when it comes to accidents or stress factors on airplanes. So the Poisson distribution because it's a whole different category of itself, are used or used with occurrences of an event over a specified period of time or interval. Here's some applications. Number of internet users logging into a website in one day. Like, for example, Starbucks uses the same process as how many people come use our free browser during the day, and how long do they spend on there? So this one possibility. So number of internet users logging into a website in one day. Number of patients arriving at an emergency room in 1 hour. Or you get the number of patients arriving at a hospital in one day. Or number of Atlantic hurricanes in 1 year. You notice it's in 1 day, in 1 hour, in 1 year. So it's a pattern we're looking for. It's usually with respect to time. Let's define this. Poisson probability distribution. A discrete probability distribution that applies to occurrences of some event over a specified period or interval. The random variable x equals the number of occurrences during that interval. The interval can be time, distance, area, volume, weight, or anything. There should be some interval. The probability of that event occurring X times over an interval as given by or by the following formula. So the probability that an event occurs X number of times over an interval is given by the probability of X is equal to, remember, it's a discrete, so it deals with population. It deals with a, not a parameter, not a statistic. So the mu is the mean, number of times that event occurs. E is a constant to the power negative mu all over X factorial. E is Euler's number, which is 2.7182818. So it's a constant number. It's an irrational constant number. But yeah, this is the formula for the probability of a Poisson distribution. Okay, and mu is the mean of the population. Okay. The requirements for the Poisson distribution there are 4 of them. The random variable X is the number of occurrences of an event in some interval the occurrences must be random. They must also be independent. Because if it's not independent, then one event will influence another, which now takes away the randomness of the entire process. And the occurrences must be uniformly distributed over the interval. So the Poisson, we're looking at the occurrences. They have to be random. They have to be independent. The occurrences of these events must be uniformly distributed. The properties of the Poisson probability distribution. There's only two of them. One, the Poisson distribution is determined only by the population mean, mu. The x values are infinite, has no upper limit, no upper limit. The parameters of the Poisson probability distribution only two of those. The mean is the population mean mu. And the standard deviation is equal to the square root of mu. So it rho equals the square root of mu. Remember, the whole calculation is determined by the mean itself. All right, let's look at our first example. Atlantic hurricanes. For 55 years, since 1960, there have been 336 Atlantic hurricanes. Actually, it's a bit more than that. This is as of like 2 or 3 years ago. Assume the Poisson distribution is suitable model. Find mu, the mean number of hurricanes per year. Okay, so the formula for the mean is the number of hurricanes divided by the number of years. That's the period of time. So we had 336 over 55 years. 6.1. Hurricanes per year. B. Find the probability that in a randomly selected year, there are exactly 8 hurricanes. That is, find P of 8, where P of X is probability of X Atlantic hurricanes in 1 year. So X is equal to 8. Mu is equal to 6.1. E is equal to 2.71828. So let's calculate P of 8. The formula was mu to the power x, e to the power negative mu over x factorial. So 6.1 to the power of 8, 2.71828 to the power of negative 6.1 over 8 factorial. Six 6.1 to the power 8 0.13, rounded 2 decimal places. 2.71828 to the power negative 6.1 8 is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320. That equals so the probability of 8 hurricanes in 1 year is that. Okay, C. It says in this 55-year period, there were exactly 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in part B? Does the Poisson distribution appear to be a good model in this case? So we found that 8 equals that's the probability of 8 hurricanes in 1 year. So if we take this probability times the 55 that have happened since, or in 55 years. So this is per year times 55 years, we get 5.9. So that's pretty close. It said actually 5 years with 8. So no. So that'd be years. So that's pretty close. The expected number of, this is number of years with 8 hurricanes. That's close to 5. So it works. So it's a good model. It found what we're looking for. Again, remember, these are estimates of future occurrences. So give or take a few points. Poisson distribution as approximation to binomial. So the Poisson distribution approximates the binomial distribution. The Poisson distribution approximates the binomial distribution when n is large. Because the more events you happen to have, the more accurate the population becomes. And when the probabilities are small. So as a rule of thumb, use this approximation if the following are true. So in other words, use the Poisson distribution to approximate the binomial distribution. If 1, the n are large, n is larger than 100, and n times p, which is the mean, is less than 10. So if both of these are true, then we can use the Poisson distribution. Okay. We can use the following formula to find the mean for the Poisson distribution. As an approximation of the binomial distribution. Mu equals NP. So if both of these are true, then we can use this approximation. Let's take an example. This is the last one of the chapter. Yay! Main pick 4 is a lottery game. In the main pick 4 game, you pay 50 cents to select a sequence of 4 digits, 0 to 9, such that you have 4 digits. It could be anything. It could be repeated numbers. It could be 0, 0, 0, 0. It could be 9, 9, 9, 9. It could be any one of those. Just 10,000 of them. It should be 9, 9, 9, 9, or 0, 0, 0, 0. Anything between there. If you play the game once every day, find the probability of winning at least once in a year with 365 days. So we're saying the N is 365 days. So between 0, 0, 0 and 9, 9, 9, 9, there are 10,000 possible numbers. And the probability of getting one right is 1 over 10,000. So first thing, are the conditions met? Is N bigger than 100? And is N times P less than 10? So in our case, N is equal to 365. So yes, it's bigger than 100. N times P, which is 365 times 1 over 10,000 equals 0.0365. Is that less than 10? Yes. All right, so now let's look what we have to do. We find at least once a year. At least once in a year. So if the only thing we don't want at least one a year or in a year. The only thing we don't want is not winning any in a year. So X equals 0. So to find the probability of at least once in a year, I find 1 minus the probability of winning nothing. So we have to find P of 0. Since the Poisson distribution, so our N is 365. Our X is 0. Our mu, which we calculate that? Yeah. Our mu is N times P, which is, we did that earlier up on top, 0.0365. That's all we need. So this is 0.0365 to the power 0, 2.8, no, 2.71828 to the power negative 0.0365. All that over 0 factorial. Anything to the 0 power is 1. (2.71828) to the power negative that becomes 0.9642. 0 factorial is 1. So the answer is 0.9642. That's the probability of not winning any. So the probability of winning at least one time is equal 1 minus P sub 0, 1 minus 0.9642 is equal to 0.0358. So that's our chance of winning at least once in a year of playing one time a day. All right, that does it for that chapter. Good luck, everybody.